and statistics. And so I think Alex's first talk of the day, pay special attention so that maybe serves also as a review and some food for thoughts for that discussion. The second one is that you see here proceedings, okay, although that's a word that has fallen a little bit out of favor, right? But the idea here is that we have a special edition of the journal Frontiers in Astronomy and Space Science Astrostatistics, to which I would like for as many of you as possible to submit a paper, and the nice thing is that first it will be refereed. It will be refereed very likely by somebody close to the field, maybe somebody in this very room, by the way, okay? So it is meant to be refereed, but, in a way that is, maybe I should use the word friendly, and also it's paid for, okay? So nowadays, every paper is, thousands of dollars, and the National Science Foundation gave us money to make this happen as well. So especially, anybody, but, I would imagine that maybe the early career, folks might, take the opportunity to have a refereed publication focusing on this. And sorry for taking a lot of time, but I also spent a little bit of time developing a LaTeX template. So the way, I just want to make it as easy as possible, right? So, and also so that we have, I would say uniform format for the papers. So it's meant to be easy, and there is more information there on the web page. So I think that would be useful if we have as many submissions as possible. And with that, I will leave it to today's first presenter. Sorry, Stephen, I need your help because without you, yeah, there you go. So, yes, Alex, take it away.
Down is next. There's a laser pointer.
Down is next.
Yeah, and stay behind the podium because the mic's in my laptop.
Okay, amazing. Cool. All right, hello everyone. Thanks for making it to the last day of talks. Very happy to be here, so I appreciate the invitation. I'm Alex Galliano, and I use generative AI to study supernovae. So the first day of our series of talks, we heard a lot from David Van Dyke about how we use supernovae for cosmological inference to determine distances. We also heard excellent talks throughout the last couple of days about how to do that accurately. I want to study the supernovae themselves. So let's talk a little bit about what we might learn from supernovae and what issues we run into that we can overcome with generative AI. Okay, starting with systematic errors that come from model misspecification, which is prevalent in many different fields. It affects us a lot in supernova science. But first, let's talk about why supernovae are interesting. Supernovae mark the endpoints of the lives of stars. I care about massive stars and their deaths as core collapse supernovae. And these explosions are the culmination of billions of years of stellar evolution, which to first order we believe we understand decently well. There are a few years that we do not understand at all, basically entirely unconstrained. And then after explosion, there are stellar remnants like black holes and neutron stars that at the lowest mass end we also understand very poorly. So supernovae are very bright, they're very distant, and for that reason, they are at the nexus of many different domains that we can study in great detail using the emission from these explosions. And so what we do is we observe a supernova get brighter and dimmer. We take measurements along what's called its light curve, as you see here in multiple different filters. And then we're meant to infer physical properties from the behavior of that emission over time, okay? So different filters, different wavelengths as a function of time. And these are the data that we collect. Okay. So what do we want to learn from supernovae? Well, it turns out that all we're really measuring is the evolution in the brightness over time and across wavelength from unresolved sources. This is a very hard problem, but we can learn a lot from the behavior of this light. And essentially what we do is we measure the properties of these light curves, and we use them to then reconstruct the underlying energy sources of these explosions. And so here are just a couple that I'm outlining here. The dominant energy source is radioactive decay of nickel-56 for the vast majority of explosions, including type 1a supernovae that are standardized and used for cosmology. But there are more exotic energy sources that we're really interested in and that we don't understand very well. One of them is a magnetar, a highly magnetized neutron star that can be formed in the explosion, and that produces a very bright and very long-lived supernova. And then interaction with surrounding material that can create a series of bumps. And so essentially what we're doing is we're taking these observations, we're trying to solve the inverse problem about the properties of the underlying engines of these explosions. But there are a couple of problems to doing this in practice. The first one is that essentially all astronomers assume that there is one dominant energy source that powers this explosion. And if you don't assume correctly, you can misspecify what's happening in the explosion and end up with severely biased parameters that are associated with this explosion. So here, I'm trying to infer the amount of mass that's ejected from this explosion, and under different models, the magnetar versus interaction with surrounding material, I get some really substantial differences in this central mass that I'm inferring. And this has implications for many different things that I'm trying to infer about the explosion. What kind of star died? What kind of compact remnant results from this explosion? So this really makes a difference in practice. And in addition, oftentimes we really don't have just one dominant energy source. We can have, for example, a magnetar whose contributions are decently weak, but then kick in at very late times. And so you can start to make out at very late times changes in the emission properties of this supernova that are not picked up by the current generation of physical models at all. And so different upcoming surveys like Vera Rubin Observatory LSST will start to have us picking out these dominant contributions and how they shift and help us find things like hidden engines. Okay, this is not something that we're currently able to model well. So enter simulation-based inference. This is a technique that I've been using over the past year or so with some excellent colleagues to try and wind back the clock and infer the physical properties to solve the inverse problem. So as we mentioned, we go from physical parameters to our series of observables. Here our light curve. And now we want to solve the inverse problem from the light curve to the constraints on our underlying physics. And I'm going to argue that you can use a generative model to do this quickly and in a calibrated way. So generative AI, I'm sure all of you are very familiar with Sora and all of the different techniques that are currently being used to sample from very complex data distributions. Here, the network is a diffusion model that goes from random Gaussian noise into highly realistic pictures of flowers. And the reason that these methods are successful is because mathematically and physically, we are very good at describing transformations from one distribution to the next. So many of these techniques have arisen out of starting from a very simple distribution and mapping it to a complex distribution that describes our data. And so the diffusion model is what I'm showing here. I'm going to use a flow-based model, which is faster and describes a continuous mapping instead of a series of discrete steps. Okay, so a flow matching algorithm, like the kind that I'm going to be using here, is, as the name describes, parameterized by a velocity field that maps from one simple distribution to a complex data distribution. It's continuous and differentiable everywhere. And the nice thing is that I can then take an individual sample from the simple distribution, integrate that velocity field, and map it to an individual sample in the more complex distribution. And so you can just see if I start from x0 from, for example, a multivariate Gaussian, I can integrate that velocity field and go to my data distribution, and I can then go back the other way around by integrating in the opposite direction. And the nice thing is that you can then use this flow to first generate samples from the data distribution by going in the forward direction, and also evaluate probabilities of individual samples by going the opposite direction. I map to the simple distribution, and then a multivariate Gaussian is very easy to use to evaluate the probabilities of individual data samples. Okay, so here I'm using a flow matching model, and I'll argue that this mapping to constrain the physical parameters is only as good as the forward model, the physical model that we used to train this network. Okay, so oftentimes we will go in flow matching or in generative AI for scientific data in general, you map back assuming some single physical model. In our case, we have 3 different physical models: interaction with surrounding material, radioactive decay of nickel, or contributions from a central magnetar. And we want some gating mechanism to say which of these scenarios is more likely, and then to constrain the physical properties of those associated models. But it's not quite that simple. This is already starting to get complex. But it turns out the problem is even more difficult because, as I mentioned, there are multiple contributions from potentially additional energy sources, and we want to evaluate, using some gating mechanism, the likelihood of any of these combinations of energy sources powering an observed light curve. Okay, and we solve this using the following network. So first, we start with our series of multiband light curves. We encode them using a transformer. And then we use a very simple multi-layer perceptron to evaluate the likelihood of each of those combinations of energy sources. And that series of probabilities gets mapped into our flow algorithm that then gives us the posterior associated with a given light curve of the physical parameters of the combination of energy sources that are most likely. Okay? And the nice thing about doing it that way, we disentangle the evaluation of the likely energy sources and their associated physical properties, which means that you can tack on a set of priors for your energy sources here. And I can say after the fact that, for example, I know a priori that magnetars are pretty rare in nature intrinsically. So even if the evidence really favors a magnetar, I want to downweight that in the contribution, and I can then just tack on explicitly at inference time a set of priors there. And these are trained jointly using an objective function. We heard about objective functions a couple of days ago, and there's some hyperparameter that determines the relative weights of the contributions from these 2 different networks. And so then at inference time, we can take a light curve and we can say which of these combinations is most likely. Here we say a magnetar and a magnetar with a radioactive nickel. Those combinations are most likely, and it's really hard to distinguish between the 2 based on the light curve alone. And then you can get the associated set of constraints from each of those model combinations. You can see here that there are additional parameters that describe the radioactive decay of nickel. And I can then get those for free. So all of these physical models are constrained at inference time in seconds. And the nice thing about this is that even if my physical model is wrong, I can then start to use the latent features of the network that I've learned to figure out how unusual a given light curve is and tell me whether I need to revisit my physical model. And so in this case, we took a transient that is powered by the disruption as a star gets too close to a supermassive black hole at the center of a galaxy. We took those light curves and we passed them into the embedding space. And you can see that almost all of them fall pretty far away from all of the light curves that we've used at training time. And so this maybe tells us in some anomaly detection framework, this is something that I should pay more attention to. Maybe I need to improve my physical models. Oops. And then finally, as we mentioned at the very beginning, we can then start to map out the physical degeneracies that people have started to see in the literature, but have not systematically explored. So here we can see that if you assume just interaction with surrounding material versus if you add a central magnetar, you infer biased physical parameters that are shared between those 2 model combinations. So this is something that I think is really, really important to start looking at, and hopefully we can now start doing this at scale with many supernovae with the Verisey-Rubin Observatory. Okay, that was a lot, but I'm now going to jump. How much time do I have?
You're good.
Okay, great. Okay, so then I will take a little bit of time to start talking about systematics that affect our observations themselves from different selection effects that we impose on training and how we might account for them in the training of our neural networks. Okay, So we have a series of physical models that describe the emission of supernovae. We have our series of light curves. But at the end of the day, our models are limited. They'll never fully describe our reality. So on the left, I'm showing a very typical plot that we look at in supernova science, the absolute magnitude on the vertical axis of our transients and the characteristic time scale on the horizontal axis. And you can see many different transients fall in this space. And we've tried very hard to generate simulations that really fill out this space, that describe how realistically diverse our observations are. And we're getting better at this. So this is a series of supernova simulations from 2010. Here is a set of simulations from 2022. You can see we're getting better at mapping out just this full space, but there will always be gaps. And to make that example really clear, here's just a radar plot of classification probabilities associated with a really weird supernovae that I was looking at recently. And you can see here that the classifier has no idea what's going on, right? It could be a superluminous supernova. It could be not a supernova at all. And we will always find events like this in nature. So what do we really do when we have a data set that is diverse and where only the majority of our events are described by a physical model that we believe we understand well? Can we do better just from the data itself? And I'll argue that when we don't have a good physical mapping and we want instead just a statistical mapping to the physics that we really care about, that we can use neural networks to do this mapping for us. And so one of the ways that we infer physics from supernovae is by taking a spectrum. Spectrum is a mapping of the emission as a function of wavelength instead of as a function of time. And you can see just how detailed the spectroscopy is for here a very typical type of supernova. There's lots that a spectrum can tell us about, for example, the chemical composition of the explosion, its energetics, the density profile of the explosion. And this is really, really important to get for as many supernovae as we can. Okay, but it takes time. Photometry, the observation of a supernova emission as a function of time, requires individual images. You can get it in seconds. Integrating as a function of wavelength takes about an hour at a fixed moment in time for a single supernova, okay? And so in practice, what we do is we will observe supernovae spectroscopically only for the closest and the brightest events. And this creates a really severe selection effect that we're still struggling to account for in our modeling of supernova light curves and spectra. And so just to bring that point home, you can really see in this mall-wide projection of the number of supernovae we've observed from 1800s to, I think, 2022 this goes to, and they're color-coded by whether or not we've gotten a spectrum for that supernova. You can see that in blue, the ones we have spectra for, we're decently keeping pace with our discovery rates until about the turn of the century, and then we really have an explosion in the ones where we will never be able to get a spectrum at all, okay? So this is a really hard problem that we want to figure out, and I want to argue that this creates a bias not in just the closest events that we now have in our training data set with light curves and spectra, but also in the underlying physics of those explosions. We're really only capturing the subset of supernovae whose physics are amenable to the brightest emission. And the ones at the lowest luminosity end of the distribution of physics are not going to be captured spectroscopically, okay? This is something that we're still trying to figure out how to solve. And so multimodal models, as they're called, which combine, for example, light curves and spectra, are starting to become really popular in machine learning. Contrastive learning is one technique to combine multiple data modalities. Jeroen and Dan talked about it earlier during the conference, and essentially how this works, it's been really popularized by language models, which can seamlessly reason over images and text, is you basically take a series of images, a series of associated texts, and I say, for a given instance, I'm going to encode both representations, and I'm going to push the representations close together in the latent space for the associated image and caption. And For all of the captions that don't describe that image, I'm going to push away from the representation of that image. And this works decently well because if I have a large enough data set, I can just say, at inference time, I have an image, I encode the image, and I look in that latent space of all the captions that lie close to it. I'm going to pluck one out. Those are a decent description of that image because they lie close together in training, okay? So this is how this is done in natural language processing. It's now being used in astrophysics. There was a very popular now example where galaxy images and galaxy spectra were encoded and aligned with contrastive learning. And you can show that you can do zero-shot prediction of spectroscopy by just encoding an image, looking at the spectra nearby, and looking at the properties of those spectra. Okay, but this doesn't work for supernova science for the exact reasons that I mentioned. If I have a training set, I embed a light curve, and then at inference time, the spectra nearby, I want to be descriptive of that supernova, but that's only going to be true if I'm sampling the brightest end of the distribution of supernovae. Otherwise, I'm going to be biasing the physics that I infer, which is not great because I really care about the rarest supernovae, which might be at the dimmest end of the explosion physics that I care about. And so to get around this, a very excellent graduate student at MIT, Yunyi Shen, and I have been working on a variation on multimodal models beyond contrastive learning. And we built what is called a multimodal mixture of experts variational autoencoder. That's a lot of pieces. Multimodal, we're encoding light curves and spectra. A variational autoencoder is just a method that encodes a representation and describes it by a distribution. The nice thing about doing that is that you can sample from that distribution. The latent space is regularized, so it has some desirable properties. You can use it as a generative model. And here, we're describing instead a mixture of experts in this latent space. So instead of just describing the latent space by a multivariate distribution, we're describing it by two. And then when we want to sample, we then sample from a mixed combination of features from both distributions. And that allows us to then learn individual properties of light curves and spectra in a factorized way, but then also the shared information between them in the latent space simultaneously. And what we find is when we do this and we train on to start a simulated sample of supernovae and their light curves and their spectra, we can put in a light curve at inference time, get out a reconstruction of what we think at peak light that spectrum looks like. And you can see the ground truth that's in red here compared to our prediction that's in blue here is much more precise than the contrastively learned prediction, which just collapses to the average spectrum in the training set. And you can see, again, this systematic offset in the prediction because I'm really biased toward bright events in my training set. And by using contrastive learning, I'm still encoding that bias. But by doing this model, I'm learning a little bit better the mapping between light curves and spectra. And so I'm more careful about what I infer, even with small sample sizes that are biased. And we can see that if we do this for many spectra across time, this same bias persists at all wavelengths in the contrastive method in orange here. Meanwhile, the spectra that we infer are unbiased in blue and very similar to the what we would get if we passed in a spectrum and then try and predict the spectrum. This is kind of our baseline estimate. And obviously our confidence interval is larger because we don't know exactly what's happening when we don't have the spectrum. They're higher than what you'd get from the spectra only VAE. But this shows that we are now inferring unbiased predictions for this spectroscopy. So we're very excited about this, and the next thing to do is to apply it to real data. So I'll just end here by saying that I'm very excited about generative AI for addressing long-standing problems that we've had in supernova science and probably in other fields, for model misspecification, where our underlying physical models are decently simplified or multi-component, and where we have really severe sampling biases in the data sets that we collect. So I showed the hierarchical SBI model. We're excited about applying this to find hidden engines, for example, and do anomaly detection. And then for our mixture of expert models, we're retraining on real data and seeing how well it can infer spectroscopy of all different types of supernovae. And thanks very much.
Yes, the name.
I was wondering why exactly does contrast doesn't fail? Is there something about it?
Yeah, it's a good question. I think so. At inference time, what you do when you have a contrastively trained model is, let's say I have, let's take the example of light curves and spectra. I just have a light curve. I don't have any spectra. I encode my light curve, and I take all the surrounding spectra in that latent space, and I take the average of it as a description for what I think is associated with that light curve. But really, I've mapped out that space, that multimodal space, based on my training set, which I know is biased toward brighter supernovae. So that multimodal space is now not fully descriptive of the brightest events and the dimmest events simultaneously, which I haven't mapped out well using contrastive learning. I think contrastive learning can be really useful when you have enough data. It's really used in data-rich regimes like natural language processing. I showed the example. And now people are starting to port it into astrophysics, and in some places it works okay, and in some it can be, I think, really dangerous.
Yes. I wonder, spectroscopy is quite expensive, but we do have multi wavelengths, like the multi-band photometry for all those light curves.
Yeah.
I wonder how much of that helps in, angle. And the secondly, it's what was my second question? Sorry, just please answer my first.
Yeah, totally. It's a very good question. And in fact, for both of these models, for the mixture of experts model and for the hierarchical SBI model, we're investigating what happens when you apply light curves from different surveys, which differ in the number of filters that you have and also the cadence. So oftentimes, these wide field photometric surveys will either have a couple of filters and you scan the sky to decently high cadence, or many filters like LSST to a cadence that's a little lower. And so we're still trying to investigate what that trade-off is and whether you can get decent enough constraints when you have more filters. So you're kind of mapping out the wavelength specific emission in more detail, but you have less temporal information, right?
Right.
And I think probably you would have, just off the top of my head, a trade-off in the way that you would expect between the constraints here versus the constraints in a single phase, in a single point in time as a function of wavelength. But that's something that we're still retraining the model to be able to do, to investigate it in detail.
Right, yeah, so the reason why I'm asking this question is because it could possibly offer guidance to the design of the filters.
Totally.
And
Yeah,
the cadence itself, so that you see that what is the minimum number of filters that we need to take to actually achieve this kind of confidence.
Totally. That's exactly right. That's actually for the hierarchical method, something that we really wanted to do as we make the simulations more and more realistic. We're trying to see at what point do we really just break down in our ability to infer the underlying physics. I think that is something exactly like you mentioned that could have bearing on how you design a survey.
Okay, and I now remember my second question.
Okay.
Type of spectral. One is the spectral transient.
Yeah.
And the other type of spectral host. So you already know, because luminosity is such an important factor in determining the explosive event, especially is such a critical information. I wonder if that is
Yeah. So it's not folded in right now. It's a really good question. Host galaxy information in general is informative, but maybe more in the prior sense, right? It's a blunt tool to study an individual explosion. And so for distance estimates, I think it could be useful if we're inferring underlying physics. I think if we're clever about the way that we factor it in, such that we're not relying on it too much, then it could be really useful. We're still trying to think about how to do that in a way that's accurate. Yeah, it's a good question.
Yeah, but very quickly, I think it was a comment by Tom there. I wonder if not sure if it was an actual question.
Oh, I think Tom is elaborating on my point that in training, we basically have this systematic bias, which then makes it hard for contrastive methods to pick up on fainter events. Yeah. Thanks, Tom.
But I'll save it for the discussion after the coffee
Great.
because it's a little more broader. Okay, thank you so much once again.
Thanks, everyone.
We have this speaker. All right, yes. Right, so Aritra will talk to us about the
Down is next.
signals under
Stay behind the
effect.
podium because of the
So,
mic, and you have until 55.
Okay, take it away.
All right. Hi, everyone. I'm Aritra. I'm a PhD student at the University of Minnesota, and this is my joint work with my advisor, Sarah. And this is detecting signals under unknown background, a geometric perspective. The name keeps changing because we're still deciding on what to call it. But yes, we do have a geometric perspective for this problem. And so to start with, whenever there is any physics discovery involved, you're usually looking for a specific signal of interest in the data, but you don't only get that signal, you are also receiving signals from other nuisance sources that you don't really care about, which actually constitutes the background. So the data generating process F can be looked at as, a convex combination of a signal density Fs and a background density Fb, and it is written as eta Fs plus 1 minus eta Fb, eta being the relative amount of signal you have in your data. So the signal search is framed as this hypothesis test. You are testing for whether eta is positive or eta is zero, zero being the null hypothesis. This test is usually performed on something called the physics data, which is the direct experimental data you're getting. And that may or may not contain the signal, and that's precisely what you're testing for. Now, this data, this physics data is directly coming from the distribution F. In our framework, we assume that the signal density is completely specified to us. We know what that is. However, we do not know what the background distribution FP is. And we have developed methodologies for two scenarios where either you have the background only data or you don't have access to a background only data at all. I will mostly be talking about the case where we do have access to a background only data. Okay, so the typical approaches in the literature always involve, mostly involve likelihood ratio tests. Problem with likelihood ratio test based methods is that they typically estimate this FP and replace it directly into the convex combination model. And let's call this estimate FB tilde. And this is typically estimated on that background only data. And the problem is that if you replace your FB with FB tilde and use this model for your likelihood estimates or likelihood ratio test, you're working under a misspecified model, meaning that this model is not what is generating the data truly. And as a result, what happens is when your data does not have any signal, you would want your estimates of eta to actually converge to zero. But due to this model misspecification, what could happen is that it could actually converge to a positive limit, which could lead to false discoveries. Also, when testing for eta is zero, your likelihood ratio test statistic has this distribution, which is half and half mixture of a point mass at zero and a chi-square 1 distribution. It is not typical chi-square 1 because you're testing for zero, which is at the boundary of your parameter space. But due to model misspecification, this distribution also gets disrupted, and you get unreliable p-values. So to demonstrate this, let's say this is our true background, right? And this is a gamma distribution. Now, you don't know what the functional form of the true background is. So you end up using a power law. Now, they are pretty close, right? And what happens if I actually sample from this gamma distribution, but use this power law distribution in the likelihood ratio and calculate the likelihood ratio test statistic? So this black line is what the distribution is supposed to look like. And the red line is the empirical distribution that we got through simulations. So you see, this completely falls off the hypothesized distribution, meaning that you get unreliable p-values, and most importantly, in this case, the line is actually below the reference distribution, and that means if you use this half and half mixture, you will underreport your p-values, which could lead to false discoveries. So what we suggest as a solution is that, yes, we also start with a misspecified background density. We call it a proposal background. We call it GB, but we don't directly use it as a background. What we do is we try to model the deviation between FB and GB. How do we do that? We first look at the space of square integrable functions with respect to this GB density, and we take an orthonormal basis for that space. And in that basis, we include this function S. S is simply Fs over GB minus 1. This S function is very important in our setting, and what this does is it detects the deviation of a density from the proposal background GB, but in the direction of the signal, because that is the only direction we really care about. And it will get clearer later what I mean by that. So what we do is we expand the ratio of FB over GB using this basis, and we have this expression for FB in terms of this basis expansion. And if we plug in this FB into this convex combination, we have a nice expansion for F as well. Now, you don't really need to care about this entire expansion. The key terms in this slide are delta and theta, the coefficients of that S function. So delta and theta are both a constant times the expectation of this S function. For theta, the expectation is under the F distribution, the mixture distribution. And for delta, the expectation is under the background distribution. So it turns out that this delta is not very unique to our setup. It also appears very implicitly in LRT-based methods. And if delta is positive, then LRT-based methods can lead to false discoveries. Okay, so let's first discuss the case where we have both the physics data, xi's coming from F, and the background only data, yi's, that is coming from FP. So remember, theta was C times this expectation of S. All we do is replace this expectation with a sample mean with respect to the xi's, the physics data. Do the same for delta. It is C times the expectation of S under FP. So we replace the expectation with respect to the sample mean with the background data. And we have a nice expression for eta in terms of theta and delta over here. So we simply use this plug-in estimator. We plug in the estimates of theta and delta, and we have this estimator of eta hat. This estimator has very tractable standard errors. So what we suggest is you divide eta hat with its standard error, and when you scale it accordingly with the sample sizes, you have just a standard normal distribution when your eta is 0, which is the under the null hypothesis. And you don't really need to care about whether you are testing at the boundary or not. This standard normal 0 is going to be there. Now, in case you don't have a background only data, in that case, the problem is that delta was actually the expectation under FP. So you cannot estimate delta anymore. And as a result, you cannot estimate theta. But if you can somehow ensure delta is negative, then theta is actually a smaller number than your actual signal proportion eta. And in that case, we suggest testing for theta instead, because that would be a more conservative test. And that way, yes, you lose the power in your test, but you at least don't make any false discoveries. And the obvious question is now, for testing theta as well, we have a very nice z-test. But the obvious question is, if you don't know how to estimate delta, then how do you ensure delta is negative? Well, for that, you have a sensitivity analysis. I'm not going to get into that, but this is the basic approach in case you don't have a background only data. Okay, so the GB, our proposal background, that can be made parameter dependent so that the choice is a little bit more data driven. If you have a parameter, you can estimate using maximum likelihood estimation. And all you need to all that changes is the standard error expressions, because you need to take care of the uncertainty in estimating those parameters. but you still have a simple z-test for testing eta. Okay, to show, to implement our method, we used a formulaic data. It's a realistic simulated data that mimics gamma ray signals from from dark matter annihilations induced in the astrophysical background. And the true data generating process is believed to be a mixture of a power law background and an exponential, Gaussian signal. And we work with the data on a log scale for better visualization. So remember, if you are working on a log scale, the power law background actually becomes an exponential background. Okay, so what we did was we fed GB an exponential model. We did not put any fixed values for the parameter. We let GB have a free parameter. We estimated on a background only data, and then we performed the test on a physics data. And this is a histogram. You can see that there is a bump over here. That's where the signal is supposed to be. We got an eta of 4.2% and almost 5 sigma significance, 4.8, right? And well, good enough. But here we are feeding the exact same, like the true functional form of the background, right? What if we change that? Well, as an alternative, we tried a Gaussian tail for the background distribution, and the parameter being the scale parameter here. There also we have pretty similar results as earlier, and we still have a 4.8 sigma significance. Now we are stretching our limits, and let's completely mess up the background specification. What if we use a uniform distribution? Turns out our results do not change much. We still have the same estimate and the same sigma significance. Now, this might seem very counterintuitive. Why would that be the case? And let me try to explain why that happens. And this is the geometric perspective that I was talking about. So this is a very crude understanding of the functional space. And when you look at this functional space, GB, whatever is your proposal background, that is always at the origin, right? Now this red dot, this is your background distribution, and this Fs is your signal distribution. So your true data generating density lies somewhere on this line because it's a convex combination of these two, and this is your F, right? So the vertical axis is the space spanned by that S function, and the horizontal axis is the space spanned by the rest of the basis functions. And your FB is somewhere over here. Now, FB and GB are different. That's why they have a positive distance in this space. But turns out that we don't really care about the distance in every direction. All we care about is the deviation between FB and GB only on this S axis. That is towards the direction of the signal, because that's the discovery that you are really interested in. So if you actually take care of this delta with a large enough background only data, that is good enough. It doesn't really matter what your GB is, because that would always be at the origin. Okay, so our method relies much less on the specification of your proposal background. And yeah, so we have identified that the conservativeness of your signal search mostly depends on the scalar parameter delta. And you don't really need to improve the specification of your entire background distribution to get a better signal search result. LRT-based methods unknowingly can end up being, anti-conservative. When you do not have a background-only data, we have a sensitivity analysis to perform, and you can still make a conservative inference. If anyone is interested, I'm happy to talk about it. And for this entire method that we discussed, it was mostly shown under the context that your data is IID. We have an extension of this entire methodology for the case where your data is bin data. So we do use Poisson model, but we still avoid likelihood estimations to estimate theta and delta. And yeah, that's pretty much it. And let me know if you have any questions.
Questions, or maybe somebody else. Where can we read more about this? Because 15 minutes, you gave a very good glimpse of something that seems extremely interesting.
Yeah, so we're still working on the manuscript. Yeah.
So my question then would be this. So this looked very counterintuitive to me, okay, or maybe somebody else as well. So what happens when your source is not fully specified, which is the more common case? So in other words, I was trying to understand how, the significance of detection. You said, if I understood correctly, okay, the significance of detection is largely independent on the background model,
Yeah.
right? But how heavily does that depend on the source being fully specified? If that's a reasonable
Heavily,
question, I'm not
because
sure.
yeah, we are right now assuming that we know where the signal is supposed to be. Like we're mostly implementing in the context of that bump hunting problem. And given that you can give us a very good idea of where that bump exactly is, we can get a Gaussian model for that signal, and we know everything about the signal density. Now, yeah, a very obvious extension of this work would be when your signal location is not specified and you are continuously looking in the entire search region. And yeah, we would need to do according, probably adjustments for multiple hypothesis testing and all that. So yeah, that would be an extension of this work. But as of now, we just assume that the signal is completely specified to us. Yeah.
Sure. It's very, very unfair. Yes, any other questions?
Do you want to show us the extra slides?
Oh, in the extra slides, I was actually showing how to do the, analysis in the case you don't have a background only data. And our idea was that we are again explaining the solution in the context of a bump hunting problem. And it turns out that delta can be ensured to be negative if you are able to dominate your, if you're able to dominate your true background with your GB in the entirety of the signal region where the bulk of the signal is supposed to lie. And for that, we propose adding a very wide and flat bump in the GB, and that's where the sensitivity analysis comes. You look at different levels of the bump, you decide on, okay, probably this is the one I should go with, and then perform the test. Yeah.
So yeah, I'm just wondering how, when you say it's fully specified, how much is it? Is it normal? You know, the signal strength, the density of the source.
No, the signal strength is what we are really estimating through eta, but we assume that you know that you can at least tell us that, okay, the signal is supposed to look like a Gaussian distribution. This is where the location is, and this is the width of the distribution. If you give us that, then yeah, it is fully
So
specified.
it sounds like everything except the normalization, so to speak. Something
Yeah,
like
yeah,
that.
exactly.
So, but then when you go to this highly specified DB, how
Well-
much does the, how good is it at recovering signal strength?
The signal strength, yeah, I think it is pretty similar to the other cases, which is around 4.2%. So there is a little bit of caveat. So when I say that it is mostly independent of the choice of GB, what happens is that we were trying to figure out whether the estimation in delta that you do somehow depends on the true distance between, like the distance between your GB and the true background, right? And what we realized is that the variance actually is minimum for delta when your delta is 0. And delta is 0 when your true background and GB are the same, right? So that's where you get the least amount of variability in estimating delta. But also what we have seen is that the variance curve actually looks like an upward, like a downward parabola. And the peak that you have, that kind of flattens out if you have more and more background data. So even if we have a delta that is positive, the variability actually goes down as you keep increasing the background data that you have. So as long as we can very efficiently estimate this delta, this difference between FB and GB in the direction of the signal, doesn't really matter where we start with. You are still going to end up having a same result. And I was myself having doubts about it. So what I did was yesterday I ran a model where the GB was actually just a Gaussian density in the signal search, in the signal region, and we still had similar estimates. So it is really very irrelevant where you start with as long as you have a large enough background sample.
And this has a very lot of potential for source detection, obviously, so, okay, but maybe we talk some more about.
Yeah,
it later.
absolutely, yeah.
Thank you very much.
Yeah.
Yes, Mayank will conclude our workshop, the presentation, and I believe that, they say in basketball, it doesn't matter who's the starting five, it's the ending five, right? The one that ended the end. So that's there's that,
Now
okay?
who's next?
So
Yeah, stay behind the podium, because that's where the mic is.
all right, Mayank.
10:05.
Hi, thank you everyone for still sticking around for the last talk of the workshop. I'm a fourth year PhD candidate at Virginia Tech, and today I'll be talking about tracing dark matter spikes around active supermassive black holes using this technique, reverberation mapping. So just to be clear, I have zero background in dark matter before the beginning of this year, but I was at dinner with Dr. Gonzalo Herrera, and he is a dark matter expert, and he started talking about dark matter. I was talking about AGN, and we realized that there is some overlap that we could work on. Now, I must give you the background that we were both quite drunk, so we might see the results of that in the slides as well. So the outline is, first we'll see what dark matter spikes are. They're a theoretical prediction. I'll get more into that. Then we'll see how black hole masses are actually determined. Then how the spikes can be traced with the reverberation mapping techniques, current results. And then obviously the main point of this workshop is the systematic uncertainties and what their effects are. So first of all, dark matter spikes, they are a theoretical prediction. So as the central black hole grows, the gravitational potential around it changes. And what that does is that if there was an initial dark matter density profile, it is also going to affect the dark matter profile, and it is going to end up changing it. So if the initial profile slope was, for example, gamma, so it's something like this, then theoretical and analytical simulations show that the gamma spike will evolve into something of this sort. The exact mathematics does not really matter here, but if you look at the dashed lines here, that is what the initial profile was supposed to be. So it would have just continued like this, but due to these spikes, this is exactly what we refer to as the spikes here. It's not much of a different when gamma is already close to 2, but as you go to smaller values, especially gamma 1, which is expected with the NFW profile, you see that there is a significant enhancement in the dark matter density in these regions that are very close to the black hole. Now, there are other processes that can destroy this dark matter spike, and that is actually something that the people who work with are really interested in, because they assume these spikes are there, and then they assume these spikes are getting destroyed, which leads to the gamma ray emission from around the AGN, from cosmic rays. So they have been using this for a long time, assuming that these spikes exist. But if you want to directly observe them, then that requires going to these very small scales, which is roughly 1,000 times the Schwarzschild radius. So we are getting very close to the black hole to understand whether these spikes are actually even there. So before we can get to that, the first thing we need to know is how are black hole masses determined actually. And it's a very simple concept. Basically, you study the motion of something that is in the deep gravitational influence of the black hole, and then use a very simple formula, assuming virial theorem, that if you know the distance of the object and if you know what its velocity is, this is how you can get the black hole mass. And this is practically how every black hole mass we know has been calculated. A best example of this is within our own galaxy for the black hole Sagittarius A star. And if you look here, they tracked the orbit of the stars that were very close to this black hole. And by analyzing the orbits, they realized, oh, there must be something here in the middle that is causing these orbits. And that's how they got the black hole mass, because black holes by definition are not detectable by light really. So this is how basically almost all masses, black hole masses are calculated. There is a problem with that though, because to get this close, you need a very high resolution. So it is only really possible for the nearest few galaxies. Even if you go to the next nearest galaxy, Andromeda, that's 1,000 times further than this is. So your resolution is going to decrease by at least 1,000. So you can't really work on resolving stellar orbits on the black holes that are at cosmological scales. So in that case, what you do is actually you take help of these active galactic nuclei. So these are actively accreting supermassive black holes that light up the material around them. So that is how we can actually observe them, because contrary to what you might think when you hear of black holes, these are the most luminous objects in the world. So in the universe, not in the world. So here is a schematic diagram of what actually an AGN is. The black hole is right here in the center. There is an accretion disk that is funneling the material into the black hole. Due to the friction and other forces, this accretion disk becomes really, really bright. And that is what lights up all the gas around it. Now, there are a lot of components here, but the accretion disk, and then there is gas around that, which is from the broad line region and the narrow line region. Then there can be jets and all those other things. But out of all these components, these are the ones that we are interested in right now. But basically, this is a schematic diagram. What does this really mean observationally? So what you observe is something like this. So this is a typical quasar spectra. There is the continuum. So this is the light that comes basically from the accretion disk. It can be reprocessed and whatnot. But this is a broad H beta line. So this is what originates in the broad line region. And these are the narrow oxygen 3 lines, which originate in the narrow line region. The key to determining black hole masses is from the BLR, because as you can see, it's rather close to the central supermassive black hole. So again, now we go back to what are needed to get the black hole mass. First of all, you need velocity. Very easy to calculate. You can typically get the width. And because this is broadened by Doppler broadening, you can very easily get an estimate of what the velocity is. What is difficult to get is the distance, because this is a line of sight spectra, right? The gas could be really anywhere. There is no way to get that until some very clever people came up with this technique, which is known as reverberation mapping. So basically what this does is it uses AGN variability to locate the BLR. And we'll understand that with the help of this. So the black hole has been bright. It's been an AGN for a while, but due to some process, maybe the accretion rate changes, maybe there is a tidal disruption event or something, which changes the luminosity of the AGN. Now the light, what we see here, so the observer is somewhere around here, you see that the AGN changes, but the AGN light from the continuum goes to the broadline region and it lights up the broadline region. But because there has to be some lag, because the light from here has to travel to the broadline region before it can come to us, we can get an estimate of how long this takes. And that really gives us the distance. A better example is here. Here is the accretion disk, here's the broadline region, and you see the variability of the continuum, which traces the accretion disk. And if you look at the variability of a broadline, you observe the pattern is very similar, but there is a lag between the two. The pattern is almost identical if you shift them by that lag, which is a very strong indication that the light is traveling from the AGN to the BLR and then coming to us. And therefore, this lag basically gives you the distance. C times the lag will give you the distance. And we find that these distances are very close. They're 10 to the power minus 3 parsecs, and they depend on the black hole mass and luminosity, but that's a good range to go off on. Now, again, we have the distance, we have the velocities. That's basically all we need to get the black hole mass. And to get rid of the proportionality constant, you have to introduce something which is called the fudge factor, which encodes the geometry of the system. So this is a point of contention. We can talk about it later, but this is between 2.8 and 5.5. So one thing to keep in mind, any black hole mass you look at, which is farther than 100 megaparsecs, without even looking at the statistical values, you know that there is a factor of 2 uncertainty just from this F alone. That is something that cannot be escaped. So always the black hole masses need to be taken with a grain of salt. So, but okay, so I've given you the background about these two different things, but how really are they coming together? So what I showed you was a very small part of the spectrum earlier. AGN actually have many, many broad lines. So they have many, many broad lines, some of which are shown here. And because they have different ionization states, they're going to be formed at slightly different distances from the AGN. The material that is the closest will obviously be the most ionized. The material that is farthest will have to be the least ionized. So the BLR is not just a single point or not a very thin system, but it is stratified. Based on how ionized the gas is, it's going to be a different location. So theoretically, if you can look at all these different lines, trace how they change, how they respond to the lag, you can create a profile of the enclosed mass, because all of them are only going to trace the mass that is inside of them. So the farther you go, you will trace a larger mass. So this could allow tests for the presence of extended mass distribution. So that is the realization we had when we were having the dinner with the wine. So that's the theoretical background. We applied it to the sample that we know. So there are 14 AGN for which we have multiple ionization lines that have been used with reverberation mapping. And we look at all of them. Here I show results from 2 of them. So basically these data points are the masses that you get from different lines. The closer ones come from helium-2 mostly. The farther ones are different Balmer lines. And you clearly see that there is something going on here. If you assume a constant mass profile, which astronomers have done for the longest time, you see that it does not really explain this point at all. And similarly here, it's a much better fit, but you still see a trend for an increasing mass. But here it's much more clearer. So we fit it with a constant mass profile, then we fit it with a dark matter profile, and we find that in our sample, 2 objects prefer a dark matter component out of 14. 4 disfavor it, and 8 really show no preference for either model. And that mainly comes from the fact that the statistical errors are quite large. As you can see, because the lower ionization line, helium-2, is quite weak. So the statistical errors, the signal to noise you get from that is going to be affected like that. If you look at the contour plots for these 2 guys, so these are the 2 parameters basically that the dark matter component depends on. And based on the fits we can get rather nice contour plots. They're not as good as we would have hoped, but they never are. So here you can trace different dark matter components. So the spike has a very narrow range. And you can see that spike is only formed for really at the edge of the contour. So so the parameter space for formation of a spike is very less. But there are other dark matter components here as well, which are more likely based on this. For this object, you can rule out a spike at this density is greater than this. So even with the large statistical error bars that we saw, this technique is already tracing parameters that you would expect, because these density values are quite similar to the first plot that I showed earlier. So it all looks good. It's not that good because there are huge systematic uncertainties. I showed you 2 examples which looked prettier because you could see an increasing mass profile, but the ugliest example is right here where you see a decreasing mass profile. There is no physical process in the world that can lead to a decreasing mass profile. So obviously this shows you that there are huge systematic uncertainties that are not being taken into account. And out of the 8 objects that strongly disfavored a dark matter component, most of them were like this, because there is nothing that can lead to this unless you have a sink of some sort. So you need even more exotic physics. An easier explanation is that we have larger uncertainties. So that's that. So what could be causing this is mainly our simplifying assumptions that we made about the BLR. First of all, it's assumed that the geometry is spherically uniform. And it is assumed that the kinematic is isotropic and virialized. That's the only way you can apply the formula. And obviously, in these extreme environments, there is a good chance that this might not be true. So is there anything that we can really do about it? The answer is maybe, because the thought is that if we have better data, and if we really do model the BLR instead of just assuming something and just applying that fudge factor, which is very aptly named, to get an estimate. So the answer maybe could be a Bayesian framework that has been proposed, and so basically what this does is, instead of just assuming geometry that just comes out of nowhere that is encoded in the fudge factor, you really look at the BLR as a whole. So this is an example of a forward modeling. You classify the BLR with some parameters, mainly here that would be the position and the velocities, and then you model the entire cloud. Obviously, you're not going to model all the million points separately, but you can get an idea of the geometry. You can model different sorts of geometries, and that could give you a better idea of the geometry of the BLR instead of just assuming that it could be one of the 2. So here is an equation that shows how this works. So basically, our idea is that the emission line responds to the continuum, and this response really depends on the geometry of the object. So in traditional reverberation mapping analysis, this thing is actually taken out, and that leads to the fudge factor. But here, actually, this thing can now be calculated. So this is the parameter that encodes the geometry of the entire thing. And if you have strong enough constraints from the data, you can actually constrain the geometry itself. So that's what the hope is, that it could be helpful. And so there are some results. For example, you can see that this model can really, because it's a very flexible model, it can really encode any type of geometry. Here, there are examples of 3 of the common ones. So you can see that it's a disk, and it's a torus, and it's like a sphere. But you can still see that it allows for all these deviations that can happen from our idealized assumptions. So these models, in theory, could offer substantial improvement in minimizing the systematic uncertainties which lead to those ugly and physical plots. But they have been limited, because the more information you want, the higher you will need the signal to noise ratio to be. And simulations show that to get a good quality, to get a black hole mass with roughly 20% error, which should be enough, you need signal to noise of 65. So, and that you're going to need for each of these lines. So for example, the higher ionization lines are going to be weaker, and to get the same singular to noise, you're going to have very deep observations. So therefore, astronomers did not really care about it, because you look at the strongest line H beta, it's going to give you a mass, and you can look at that in a much less time than it would need for the weaker line. So they were all happy with it. And that's why to date, there has not been many studies except for one object, which is a very funny story, and I can get into that later. But most of the analysis has only been limited to the strongest Balmer lines. And obviously, if you have only one line, you cannot create a mass profile. So this also leaves open the possibility of another systematic uncertainty in determining the black hole masses, which is the presence of an extended mass profile due to the dark matter component. So the reality as of now is the dark matter side is assuming that there is a dark matter component. They're creating their models based on that. They're saying that this will lead to the formation of gamma rays, cosmic rays, and they're running with it. Astronomers, on the other hand, are assuming that the mass is constant, and then they're running with it. Obviously, these two cannot be true at the same time, but both these people, they're working on it. So as long as we can get data that can help disentangle between these two scenarios, the two sides will just keep running with what they want to assume, and we won't actually know what is happening. Now, modeling of higher ionization lines can help in eliminating this uncertainty, but it still remains to be seen whether the uncertainties can be made low enough to put really any meaningful constraints on the dark matter component. So that's basically all I have. I'll go through the summary quickly. So adiabatic growth of black holes predict the formation of a dark matter spike, as we saw in the first slide. And this is supposed to happen at sub-parsec scales. The realization is that reverberation mapping, which is the main technique for getting black hole masses, also traces very similar scales. So if these two techniques same similar scale, you can apply them together and see what you get. Current observations offer a mixed bag of results, and obviously they cannot be trusted with the plot I showed you. But the good thing is that they still show constraints that are close to the theoretical predictions. So if with time we can reduce the systematic uncertainties, they're only bound to get better. But again, as I showed, the large systematic uncertainties are really that they cannot allow us to make any conclusive remarks. A Bayesian modeling approach offers the best way to tackle these, but the application has been very limited. An observation of high ionization lines, it is going to be very resource intensive, but it could lead to a clearer physical picture of what's actually happening very close to the black holes. And thank you.
Yes,
Yes.
Very clever use of the reverberation mapping and to actually probe the inner profile of dark matter. And I really appreciate that you also acknowledge the systematic effects. Some people just show their what actually works. So it's refreshing to actually see that the unphysical profile itself. So I have two questions, and the one is that in terms of data for that kind of scale, and nowadays we have ESO has gravity, has those interferometers. And also in the US, we have the large binocular telescopes that are actually operating in the interferometer mode, so that we can actually resolve the Bell vibration. And that kind of information has been around for about a couple of years from the gravity team for the nearest quasar, like 3C273.
Yeah, 2018 results.
Yes. So those information can be folded in with your with the reverberation mapping data to actually constrain probably better of the geometry. I wonder, what's your thought on the prospects of interferometer in actually aiding this line of research?
That's an excellent question, and I did not include it here, but yes, there has been an unbelievable advancement. In 2018, they were able to actually basically get a photo of the resolved spectroscopy of the BLR. So definitely we are getting there, but again, these in those results, they only focused on one line. So they only focused on, I think, Paschen and one of the lines in the IR. The problem is all these interferometers work in the IR, and the lines get sparse as you go farther down. So mainly these high ionization lines are in optical and in UV. So you can go to helium-2, carbon-4, Lyman alpha. The farther you go, the higher ionization lines get weaker. So it gets even more difficult. But definitely, I mean, you can get still Paschen beta also traces a slightly different region than Balmer. So if we can get basically observations for a single object, reverberation mapping, and resolved BLR, that would be amazing. Yes.
Okay, great. Yeah, and then my second question is that in this kind of unbody system, the morphology is not completely decoupled from the underlying distribution of matter. So because the two are interconnected, and so in your framework that you showed, and you wanted to have this kind of non-spherical distributions of the clouds. I wonder, because the underlying invisible mass distribution is something that to be inferred, and that will actually change the morphology of the clouds. How do you plan to actually disentangle this?
So the good thing with that is the BLR, the accretion disk, they all account to 1 or 2% of the total black hole mass, right? So the mass of the BLR itself is not going to affect the enclosed mass profile a lot. So really the position of the material does not matter. The geometry matters because it affects how the cloud is illuminated and how much the delay is going to be. Because if it's not spherical and if particles are at different positions, their illumination profile is going to be different. Each particle will be illuminated after slightly smaller time. So the geometry basically matters for that. The mass distribution does not really matter because results have shown that the BLR itself is only 1% of the total black hole mass. So yeah, definitely that uncertainty is almost always going to be there. But if we could get down to 2%, I'll call that good.
Yeah, I think I'm mainly concerned about the orbits of those things that are in that kind of gravitational potential. And when you actually change the potential, the law of the morphologies of the orbits are going to be different. And because without orbits, you don't have the morphology that you see. So, but on the other hand, there is also this thing that is from the AGN itself, but it will actually influence the ionization of the clouds. And so the distribution, the morphology that you assume for the cloud distribution will also affect the photoionization results. So there is also photoionization which causes different lines to appear at distribution, right?
Sorry.
Yeah, go ahead.
So yeah, people have thought of that, and that's why. So these two papers from earlier, they mainly focused on the geometry. Rosborough et al. For 2024, and there are a couple more models who are also taking that into account. So they are also including cloudy models into this whole thing. So it's not just about geometry now. We really want to create a physical picture. I don't blame the astronomers. I'm one for assuming the mass is constant. But even before this, I mean, it's something that we just came up with. It might not even mean anything. They were already trying to get closer and get a better physical picture just for the sake of it, even if they assume that H feature traces the original mass. So there have been efforts for that, and yes, definitely.
Okay. I'm just wondering, is EHD likely to be used?
That's a good question, but yes, I don't think the band that it would, because it will be in radio, right? So in radio, these emission lines really are not going to be very bright because most of these.
I mean, you don't have to actually rely on emission lines. You can probably solve these bumps directly.
Yeah, I think it's going to be difficult because even if you go to Andromeda, it's 1,000 times farther than our galactic center, right? So the resolution is already worse by 1,000. So there is, as is talking about, there are new techniques that do that. So there is gravity collaboration in which VLT is creating something of that sort. So, and they have been able to go down to 10 to the power -4 parsec in some of the nearest galaxies, which are also AGN. So that definitely has, it's not exactly EHT, but it's extension of that. And that definitely has some good potential. Yes.
Okay, so in that case, thank you very much again, Mayank, and I suppose everybody. This is before we take a short break. This is really the opportunity. I believe there are a few of you also on Zoom, and this is an opportunity to thank you all for being here. Okay, I guess in order of importance of the reason for the success of this is that, well, you all came here, okay, right? Either in person by plane, boat, or car, or by Zoom, okay? Anyway, without you, this would simply not be possible, okay? And it's been really nice to see how over the years, the NSF, I have to say, has been supporting these efforts for for conferences. I'll tell you how many proposals I put in for doing the science and how many no's I've got, all of them. But every time I ask for money for bringing early career scientists and even senior scientists for a conference, they always cut a check for me. So, that's really very much appreciated. And it's nice. And hopefully that will continue in the future. And of course, I see, Stephen, Kishan, and all the others in the, I guess, local organizing committee. I mean, yes, okay. So, without a hitch for days. So I really appreciated your help. Okay, including setting the tables and making it happen. Wonderful. So thank you so much. With that, I would suggest that maybe we take a short break, get a cup of coffee, maybe come back and in a few minutes instead of waiting whatever you said here on the program. Maybe come back and start the panel. So that way, might be easier for anybody who needs to get back home instead of waiting around. Okay, so yeah, let's just get a cup of coffee and maybe come back. Too much, right? Sorry.
I mean, it's not that hard. I mean.
So please come here and then tell us. Yes. Oh, there you go. I set him up just like that.
Making these provocative statements until you've gone through this thing about the journals, but I'll make the provocative statement.
Tom just wrote something online. He said he understands the limitations of being on Zoom, but in some cases he's been able to hear the room talk. So if we just talk loud from the back, it might pick it up, especially because I moved the camera closer, or the microphone closer.
Okay.
Excellent.
Great.
Okay. So provocative statement. So generally speaking, people don't or have not made a big distinction between astrostatistics and ML AI techniques, generally speaking. But my provocative statement is maybe we should. These techniques are quite different and they aim at different things. And one of the major issues that AI has to deal with are these epistemic uncertainties that Tom Loredo mentioned yesterday. And in astrostatistics, around 30 years ago, I suppose, people started paying attention to actual Bayesian analysis. Around 20 years ago, people started dealing with appropriate likelihoods, like using Poisson for counts data as opposed to making Gaussian approximations. So maybe the time now is to start applying astrostatistics or statistical methods more rigorously to AI systems. I mean, we've seen a lot of that happen during this conference. I mean, there was this what was it, adaptive learning, right? For the is it adaptive learning? Whatever it's called, yes. Which tries to move and make the coverage intervals more robust, right? That's one way of looking at it, right? So I think there are things that are happening that are going along this direction. So I think we should just encourage it. Max, that should be that's your goal for the next conference, I think.
Oh, I see. I should have been taking notes. Well, maybe you will keep helping me, so I don't need to take notes. But
anyway, that is my provocative statement, such as it is. That I think that you need to bring in more statistical rigor, statistics, formal statistical formalisms. Into AI.
I would say in the spirit of just talking over coffee, right? One thing that I take away from this meeting is that actually how much statistics we heard about from the, I'm going to say AI people, right? Meaning that I'm not one of them, so I feel like I'm learning, right? So yeah. And that's also when I think one of the items that I had there, I called it chicken and egg problem. I'm not entirely sure what I meant by that, but probably, yeah, which one, drives the bus, so to speak. So I'm not entirely sure I have anything else to contribute, but
yeah, I'll maybe just add. I think it's tough right now. We're in a landscape where so many of these AI techniques are co-opted from industry, where they have been very successful at specific tasks that are in some ways misaligned with the objectives in many scientific disciplines, right? We care about calibration of our predictions and all of these things that, like, if you're just looking at an image, you'll say this model is very successful and you really don't care to investigate further.
Right.
And I think that's a problem. And there are many different things that contribute to those issues. I think the funding landscape is a little broken right now. And so, yeah, I think that applying statistical thinking to generative AI is super, super useful, especially as these tools become easier and easier to use out of the box, which is like amazing. It's a great thing and should be encouraged. But at the same time, I think it's a little bit of a problem when you have both professors and junior folks alike wanting to throw a neural network at a problem and then
But I think
get a prediction.
yeah, the one thing that comes to mind is that obviously sometimes you have a very broad projects in which obviously you cannot fine tune the nuts and bolts of every single. How do I put it? If you want to generate extensive data, images, right? You take care of the statistics. What can I say? As much as you can, because the task is so complete. I'm not sure if I'm putting it in a right way, and then maybe some of the not anyway. But so yeah, Tom, I believe you can also speak if you would like. Yes.
Oh, okay. Can you hear me?
Oh yeah,
Yeah.
just fine. Yeah.
Perfectly.
Great. So I was going to say I really appreciated Vinay's comment, and I think one area where it seems to me there's a great opportunity for kind of back and forth between machine learning and statistics is functional data analysis. This is the area of statistics that tries to formulate problems that involve populations of functions as opposed to multivariate statistics where the populations are of vectors or textbook statistics where it's usually populations of scalars. So populations of functions would be populations of light curves, of spectra, of images. And so this is a very well-developed area of statistics. It really got its start in the 90s, and it's one of the big areas of research now. And there's been very little crosstalk between that and deep learning. There's just maybe a dozen papers that try to put together ideas from FDA, as it's called, and deep learning. FDA is also just by itself is rather new in astronomy. I have a review article that's probably going to come out in about a week or two on Archive, where I review opportunities for FDA in astronomy and try to make the connection to foundation models, not with any actual work in that last part, but pointing out the opportunity. It just seems to me this is astronomy in particular, with this abundance of functional, what statisticians would call functional data, ensembles of light curves and spectra, and even images, which would be called so-called next generation functional data because they're multivariate. I think there's a big opportunity there that nobody is yet exploiting. That's my comment.
Tom, do you have, or either of you have thoughts about how to incentivize that kind of interdisciplinary work?
I'm aware of one paper which might be in along that direction. That's by Yang Song. I don't know if you've seen this, Tom, or
No,
right?
the name doesn't ring a bell. No.
It's actually Yang Song. I mean, he was a student at Harvard, along with Rafael Martinez Galarza, Ashley Villar. What they did was they tried to model light curves through what's the thing, Poisson variational autoencoder.
Mhm.
So you would essentially modeling the latent space and extracting families of light curves that way. And primarily, if I remember right, they were just sinusoids. So sort of like a Fourier transform. So I don't know if, if this is the kind of thing you're thinking of.
Yeah, I just found the paper. I'll definitely have a look. So one of the projects that I've worked on that this review paper describes. So actually, so a great example of functional data analysis in astronomy is the Casey Mandel's approach to modeling supernova 1A light curves. It's where he uses Gaussian processes not to model light curves individually, but to build a hierarchical model for light curves. So that's called Gaussian process functional data analysis. He didn't know the term, but that's what he's doing. Another application is work I've been doing. It's motivated by photometric redshifts, which is trying to come up with a data-driven model for that, a data-driven parametric model for galaxy spectra. And so in the work we're doing, we're pulling together pieces from the FDA literature and from the machine learning literature. We're building a latent representation with a dimension reduction, a manifold learning method called FATE. But so that's a place where, one way to do this kind of merging of ideas is to just take pieces from each of these fields and put them together. There might be a more unified way to try to bring FDA into machine learning, but yeah, those are examples. So yeah, so Casey's work with Gaussian processes, which is on the boundary between machine learning and statistics, and then the work we've been doing on SED modeling, which is just kind of a piecemeal approach. So yeah, I found Song's paper, a Poisson process autodecoder for X-ray sources.
That's the one, right?
I'll drop the link in Slack in case people are interested in following up on this. I'll also drop a link in there. I have a short version of this review paper I mentioned. It just got published. It's already on archive, but there's a much longer version that will be out in a couple weeks.
That's great.
Where is it going to be published, Tom?
So the short paper is in Physical Sciences Forum. This is a talk that I gave at a Maxent meeting. That's the proceedings issue, and then they invited us to do a longer version of it for the journal Entropy. It's cross-disciplinary, so hopefully, I'm late for their deadline, so hopefully they'll still accept it, but we'll put it somewhere if not there.
Oh yeah, I mean, I was just going to add, I think there's so much room for bespoke neural network techniques that leverage like traditional statistics to be more amenable to the specific types of data that we collect and analyze. But again, incentivizing that research, it's not entirely clear to me. There's so much money right now in industry that's being pumped toward generative AI and to very impressive results. And so being able to fund that type of very interdisciplinary research is one thing, but then the other thing is how do you train students at that interface between domains, because it requires a lot of traditional statistical training, right? It requires knowledge of machine learning. It requires a lot of domain expertise. And so I think, yeah, right now, the siloing that happens in academia might not be amenable to
Yeah, that's
mass
yeah,
development.
right. That's definitely yeah. Go ahead.
This
Right.
is, yeah. No, it would be interesting to bring up the ISTAT workshop at Imperial last year. Because I think the theme was machine learning in statistics or something like that. The original title was written over a quote of like what can statistics use for learning. So yeah, it was Louis Lance it was a very interesting workshop where I think simulation inference, of course, was the major theme precisely by the team. Yeah, but there were like, so for example, I brought up this question of neural network uncertainties. We're going to get likenesses from neural networks. How are you going to quantify that? There are these things built in networks supposed to cause uncertainties, but they're not very reliable. And in fact, that led to a very interesting paper by Jesse Taylor, who actually showed that you can get very reliable 95% function intervals. I think the kind of thing you're talking about is, yeah, there are now some forums that we expect that. Like James and I started talking also based on that same workshop, but getting reliable uncertainties in-house.
Yeah, and I was wondering, following up on your comment, Alex, on having been a professor for so long, right? And that, what would be useful to train better? I mean, I guess people know how to train statisticians, right? People know how to train, let's say, data analysts, and certainly they know how to train machine learning people from our computer science department, who has like 10 courses, right? But maybe somebody who knows both, what would help? I bring it up because actually here at UH we are in the process of establishing a quote data science unquote program, masters and maybe a PhD. So we don't have one that, I wonder, how do we how could we do this best? Because yeah, I don't know. Certainly everybody needs to know a little bit of likely ratio testing. I think probably that will continue to be true no matter almost what, right? But maybe courses in AI are slow. We are slow in academia, right? That we pride ourselves in being slow, right? Because we like it that way, and maybe because we are lazy or whatever, right? But maybe
careful. We are careful. That is
Oh, so sorry, Vinay. Yes, we are being careful. Oh, yes. So sorry, my English isn't that good. Yeah, that's what I meant. Yes. Didn't mean to use the L word. Yes. Uh, and I wonder, or maybe people don't really need courses. Maybe they just need to, they do it as part of thesis or dissertation. I don't know, because at the end of the day, right, that's where most of us learn, the ropes, right? Mm, I know that there are, of course, data, AI. I mean, masters and PhD programs almost, everywhere. But maybe most of us, I would say, and probably how many of us are training? I mean, we have done or are doing traditional PhDs in physics and astronomy, right? Maybe some of you are in some programs that have the data science name in them. I don't know. I wonder. Maybe nobody. I'm just, is a relatively reasonable sample. Maybe I don't know. Maybe we're already doing the right thing. I don't know. Or maybe we need different programs. Any thoughts?
so. Sorry, if there are any.
I guess I'll offer what I can represent myself. I'm in the statistics data science department, but among statisticians, we don't tend to have that much experience training neural networks. It's something that I learned by practicing. And I suspect that the best way to learn how to deploy these increasingly complex machine learning models is by having just a team of people who are willing to actually sift through the loss curves and say, yeah, I think we're miscalibrated, or we're not doing the right regularization, this sort of thing. I don't think you can learn that in a course. I think you really learn by doing, and you learn by doing, I think, with the team, because it's really hard to figure that stuff out on your own as a grad student, and in the basement of college, wherever it is.
It's always in the basement, isn't it?
Yeah, the business people get the fourth floor with the windows, and then we got the basements. Yes.
Underpinning for that, both they have to build their own learning project, and also actually they can take whatever project they're doing. So for example, some students that are doing lots of sort of learning, and then they think, I want to apply it to astrophysical data. And then they have to look out for which group they want to collaborate with, but they have a lot of opportunities just to pick which subject interests them, and then they really put it into practice for them. So I think that way, where you combine the theory in your lectures and then have applications at home, then you kind of learn immediately how you can yeah, incorporate all sys2025.
Yeah, I'm glad to hear. There are at least a handful of students who, over the years, have taken my class in which on that analysis, and we try to do exactly that. And I believe that, I mean, I don't know, you can speak up, but maybe you only learn MCMC when you do it at home because I give you a home. You do it as your project because sure, you can lecture about Metropolis Hastings, but it comes alive when you have your data and yeah. Okay, so. I share your comment. Yes, by all means. And
Oh, that's okay. With things like MCMC and especially machine learning, you can learn so much in a classroom, but there's also an art to it. Yeah. That unless you're hands-on and you play with it, you're not going to get it. There's something intrinsic about it that is fine-tuned to every problem. It's always different, and you need to figure out how to turn the knobs yourself in order to get it to work.
yes.
Even in MCMC, which is very well known and easy to play with, there's always something that the code works, but you need to tweak certain things that are problem specific.
That's also because machine learning is moving so quickly that a lot is heuristics right now, right? We see phenomena arise that we still don't fully understand. And so we can't really formalize this in a course and say, this is what you should be doing, and here's why. We just say, train a model and you'll figure it out.
Yeah, and besides, it takes about, at least my institution, a couple of years to get a course approved. By the time that happens, that's right. So this is like
Well,
having the
okay,
cake and eating it too. Yeah.
Let me change that question slightly and ask, for the machine learning, the AI people, what sort of statistics course do you think would be helpful? And vice versa, for the stats people, what sort of machine learning courses do you think would be helpful? If you guys especially wanted to take a specific stats course, what do you think would be most useful?
Maybe another way to rephrase it is that, let's say you want to get a grad student involved. Maybe you would like to pick a grad student who has taken a course in what?
Yes.
Maybe that's the way to put it,
Yeah.
or maybe ask them to take the class, whatever,
Yeah.
But for an AI person, what courses do you think that it might be useful to have? I don't know. Yeah.
That like it might seem a little bit dramatic, but that also shows you how it's like model specification. For example, in most of the cases, we see that when people use likely regression, people use the Fisher inverse form and estimate the variables. But very few people realize that when you have a misspecified model, that is a wrong formula, and it could be undershooting or overshooting standard error. And if you just take the first class, you know that due to this misspecification, things change slightly, and those are not really that difficult to estimate. So I think first level mathematical statistics could be used for anyone who wants to.
Yeah, I would definitely agree with that. Yes, absolutely.
I think for the students who that I usually work with, when I looked at all the basic quantitative course things with the stats and maybe even quantum mechanics or any of those that actually have a lot of quantitative basics, and then whether they have taken intro to deep learning or not, I think that matters less because you can learn it on the fly as long as you have the mathematical basics, then you can just dive into it. And then like in the projects we do with them, then they learn some astrophysics along the way as well, while at the same time they interact with other people at the team who've already trained in learning networks, and then by actually have to bring the right amount of people together, you easily learn how that works.
Yeah, great.
Biased, but all the courses surrounding Bayesian inference for me is so useful. Yeah, just to have people who really understand like what they're trying to predict and how they know when it's a model is doing well or doing poorly, and not just satisfied with like an individual prediction. And then also linear algebra, super useful for actual training of neural networks, and I feel like it's really underappreciated.
Yeah, linear algebra, you bet. Yeah.
So At some point, we started a course on machine learning for particle physics because we realized that thing that we realized that your data is very specific and there are a whole bunch of tricks that you need to learn, and you just do a use case assignment very quick. And you did this, that's not going to translate to your problem. For example, in particle physics, we have masses that are sharply peaked, and you want to handle sharply peaked very well. Like there are many problems that we have. I was wondering, naturally, you have these kind of features that are like obvious things that this is something that will not just work out the box and
Nothing works out of the box.
Yeah.
I would like to, I mean, maybe it's because I'm from a strong program, but there is, like as you said, machine learning for particle physicists. It'd be good to have machine learning for astronomers program or something of that sort. Maybe there is one that I've not heard, but just to get a hands-on experience that, it's not very easily achievable with just courses. Just getting, because the first thing is, the hardest thing is realizing when your research could benefit from machine learning. If you're doing it with traditional techniques as of now, when do you decide that it would be worth it to put the time to learn machine learning because it would help your research that much? But there is no, I mean, at least I couldn't find something like that.
But I think that the challenge there, speaking like, I guess an older academic, right, is that, well, I mean, right, is that it requires that teachers, right, actually know that, right, that have done research in that. And frankly, that, right, that there is a big gap of several years by the time, you do your doctorate and and you got a faculty job, and then all of a sudden, for example, I'm let's say more than halfway through my career, right? The things that were hot when I was a postdoc or early career, they aren't hot anymore, right? And frankly, I haven't kept up with, right, everything at all, right? So I can kind of see how the challenge comes about, right? And but maybe, it's nice when, literally people who are more in touch with the immediate, research also, teach those courses. I don't think there is a fix for that because right, anyway, so I wanted to make that comment.
This is why on the side of learning by doing, I'm a big fan of the AI Institute. It's obviously also very biased, but IFI at MIT, it's MIT, Northeastern, Tufts, and Harvard, and brings together computer scientists and physicists and statisticians, and just having those people in the room, you tend to talk about the things that you're working on, and so by diffusion, you start to pick up on some of these things and how they might be useful for your own problems. And I don't want to malign NSF because it's the reason we're all here, but I've heard time and time again that funding proposals, like, they're very conservative. And so
yes, they
very conservative.
Yes.
And I think when you're resource constrained, the problem gets even worse, but it's just really hard when all of these things are very new, and there is no substitute for just having the money to get the people in the room to have these conversations.
And have the money quickly. No, not 6 months. Anyway, yeah, one announcement every year, 6 months to write the proposal and 6 months to get it back. But Tom, you had a question, I believe, or your hand raised. Sorry, maybe. Yeah,
Yeah, just a comment. It's just kind of a idea to throwing out there about this training. I have a joint appointment in statistics. My main position's in astronomy, of course, but and one of the things I do there is participate in a master's. We have a master's of professional studies program, so people who come in for a 2-year degree to go right into industry. And it has an interesting course. It's a 1-semester course where the students are put in teams of about 5. And for that semester, they work together with their advisor, me or other people, on a problem that's usually posed by somebody from industry who's recruited to participate in the program, though sometimes it's other people on campus who need some statistics consulting for their for an academic problem, but they're mostly industry problems. So of course, to do that is a huge amount of work to arrange industry sponsors, but I'm just wondering if, so this is triggered by all this, but many people recognizing that you learn by doing. I wonder if there's a way to build astronomy courses that link, that put a couple astronomers together with maybe some students from computer science or statistics or both, and just try to work on a problem for a semester.
Yeah, I mean, you
there
usually
are-
what gets in the way is that, sometimes you have a student who needs to have a course and he gets the credit only for a department. There are little tiny, very annoying details that over the years, they keep coming up. They get in the way of doing, yeah, just that. But that seems the way, yeah, to do it. Sorry, no, I interrupt.
No, you didn't interrupt. I don't know how to make this happen. It would require coordination across departments, which, it's happened at Cornell for the MPS program, but it's partly, to be a little cynical, it's partly because that program has students who pay full tuition. It's actually a moneymaker for the college. And so there's a significant financial incentive to make it work. So how do you build that incentive into other departments? I don't know.
So Tom, that's actually been the model for CHASC.
Uh-huh.
What we do is, well, what we mean, Shangli has this seminar course, and everyone who takes the seminar course is required to do a project, usually with an astronomer in attendance.
So CHASC, for those who don't know, sorry.
Go ahead. Yeah.
No, you go ahead, explain.
CHASC is it
Consort.
stands for the CHASC Astrostatistics Collaboration.
It's a recursive acronym.
it's
California, Harvard, it was originally,
Really?
but
Once
not
upon a
anymore.
time, it was the Chandra Astrostatistics Cabal.
Oh.
That was better.
That's-
name. I love it.
It's a collaboration between high energy astro people from at the CFA, where I'm from, and Harvard statisticians, and now it's expanded to be worldwide. Lots of statisticians everywhere from California to Imperial and points in between. And we try to. So the way it usually works is, astronomers tend to bring an analysis problem, and statisticians throw students at it, and usually something good happens.
Yeah, I mean,
Do students get credit for that?
Oh, they get their PhD out of it.
yeah.
Yeah, they usually write papers, usually as first authors. So yeah, they get a full project out of it.
Yeah, sometimes the challenge there are relatively smaller institutions, frankly, like mine, and others, is that it's really hard to put together a team like that. I was, sometimes we just don't have that many, yeah, anyway, but that I can see how the big advantages of doing it. Yeah. Yeah, please go ahead. Yeah, Samuel, please, you're free to.
Oh, okay, great. Thanks. Yeah, I just wanted to add that I think something that's been helpful for me is there have been some students who I've taught in my astronomy course, but who haven't been astronomy majors. They've been majors in like computer science or some other sort of STEM discipline. And I found that those students who are also interested in research tend to be some of the most productive astronomy researchers in the group, because that having all of that sort of computer science and statistics background really helps them hit the ground running when it comes to research. And then all I have to do is teach them the astronomy, which I'm very confident in. And so that's been really productive. And so maybe there's something that we could do to get more students who are, interested in computer science and statistics, more interested in astronomy, or maybe vice versa, include more of those sort of similar skills in astronomy curricula, so that further down the line, these sorts of cross collaborations are easier to coordinate.
Yeah, and the thing that comes to mind is that there is a mutual, advantage, meaning that, all for astronomers, jobs are not easy to come by, right? But, but maybe, in academia, I should say, but probably, the training for an astronomer in machine learning AI as its obvious advantages. So, I can see how, that, you may get more astronomers excited about collaborations.
On the funding side, Tom, there was a little nugget in your last response where you mentioned industry sponsors in your program. What does that look like? How did you get the sponsors? And is that a model that could be adopted elsewhere?
Yeah, that's what I was trying to get at that when I mentioned that it's a moneymaker for the college. So they actually have a faculty member whose main job is to direct this program. So he spends a lot of his time, finding these industry sponsors. And he doesn't have a lot of trouble doing it because they're getting free expertise. There's a faculty member at the head of each group, so it's not just students kind of randomly guessing solutions to problems. There's expertise brought to bear. But yeah, like I said, there's a faculty member that spends basically his full time trying to make this work.
And it to me makes sense, we were also having, talking about the NSF being somewhat slow at times, let's just put it like that. And yeah, and maybe that's the way it is, meaning that, National Science Foundation is great, but then there is industry partners. And but incidentally, since we happen to be in Huntsville, at least most of us today, here in Huntsville itself, which is a relatively small university, but we have an incredible number of companies in the area, government contractors. So there have been fields in which we've been very successful in attracting money from industry because I also the scale of money is different, right? For many industries, drop in a few millions is a drop in the bucket, but for the NSF, it isn't. And so maybe things sort themselves out that way.
Right. And folks that I've talked to in industry, everyone wants to take part in a scientific discovery, right? Everyone wants to be involved in that process. And so if there is some mutually beneficial exchange to be had, I think more departments should pursue those avenues.
Yeah, and the student training, maybe do science for a few years and then work in industry. I personally have experience with many of my students. Most of my grad students ended up in industry. They stayed in Huntsville, as it turns out, just like me. Huntsville is like a black hole. It swallows you. For many of us, it did that. Okay. Anyways, but that's just a side comment.
The idea for connecting the statistics, AI, and astronomy was a research project I proposed at the time, and the people I was working with, they were convinced with phase, we don't need AI. This is what we've done, this is what we're going to do. So it kind of, fell off. But my idea was, I work with an active satellite. We see a bunch of things in our data, a bunch of different source types. And I thought the easiest thing to do would be a CNN convolutional neural network, which if you were to teach a class on that, that's the easiest math to do. I did the math at home and you can understand it, you can apply it, and differentiating source types is relatively easy and straightforward. They're very different, so it should work relatively easily. And to connect this to students who aren't astronomy majors, they need data. They want data to play with. We have a ton of data. And the easiest way is we see these different things. They're very different in very different ways. And they're very easy for us to just look at a light curve or look at a spectrum and go, I know what that is. So make your model learn that, and it should be relatively robust at differentiating. I feel like you could almost do that with gamma ray data, X-ray data, whatever type of data you want in a semester. You can teach the background of math, which people who aren't astronomy majors might already know. People who are astronomy majors will learn and be happy with. And then you get the data analysis part, and the astronomy majors will be happy to play with the data because they like it, and they're learning AI. And the people who already know CNNs and everything, now they have data and they just have to learn a few systematic things. It's balanced on both ends, the front end for one side and the back end for the other, and it connects it.
Yeah, pretty much we are all saying that, collaboration is the only way because it's impossible to have, one person, know-it-all professor who knows everything, right? You know, it's yeah. Um, I wonder if you want to switch slightly gear and talk about publications. I don't know.
Oh,
I
yeah,
mean,
yeah,
I'm,
yeah,
you know,
that's-
I'm just, you know, no, I don't
No,
want
that's-
to drive necessarily.
Past 11, so yeah.
Yeah, it's already 11, and you know, let me just, I jotted down this morning, okay, and I'm not entirely sure how comprehensive it is, but I believe that, for example, I was looking at the Scargill's papers on Bayesian blocks, right? They were published in APJ, right? You know, that to me says kind of everything that you need to say, meaning that, you know, lots of theory goes through papers, or lots of statistical theory goes through papers that get one random referee, right, who might know some statistics, might know no statistics, or might know the wrong statistics, right, you know, or the good. Anyway, you get the message. So that's how I often publish sometimes when I have some of the things that I showed you earlier. Anyway, and right, and so in other words, you know, APJ, ANA, monthly notices, I mean, just to name a few, basically there is no emphasis on refereeing of the statistics part. Of course, I believe that actually APJ does have an editor who is dedicated to statistics pay, but in,
No, if he still is. I mean, it used to be Eric Feigelson who would look at every paper for statistical content.
no, we were Eric. No, I think it. Well, I should have remembered the name because he handled both the papers. But anyway,
It was Eric for many years. Yeah.
yeah,
But
yeah.
Is there still one, Tom? Do you know if
I
there's
I
a?
don't think
I don't
there-
know.
but you know, bottom line is that anyway. So and there is definitely no you know, not even a section on astrostatistics, right? You know, so anyway, that's or same for physics. Like, you know, there are a lot of papers, you know, methods for particle physics. And then, you know, the opposite end is that, you know, good luck for an astronomer like me publishing in the Journal of Astronomical, sorry, of the American Statistical Association. I could not pull that off if I tried, right? You know, and that's just the way it is, right? You know, Vinay and I were talking that we have co-authors on a paper with a bunch of statisticians. It's been taking 3 years to write it. It will take 2 years to get it through, maybe, you know, and you know, maybe I'm exaggerating, but you know, I think it's about right, you know, and also the system of refereeing is different, right? You know, I believe that in most, if not all, and that's an open question for the statisticians here, you know, usually you got at least 2 referees, right? You know, and so obviously maybe at least quadruples the, you know, not the problem, is a good problem anyway. So that's how it takes long, is different. And I will point out that let's see, how do I scroll this down? Can you move it, Stephen, to the next page, because I seem to be stuck here. But so sorry, I'm just
Just to give a kind of specific example, since you mentioned AOAS there, I was an associate editor there for 18 years. And you're right, it's a pretty thorough review process. Every paper had 2 referees, a statistician, and somebody from the discipline area. And then the associate editor also wrote a report. The associate editor just didn't manage the reviews. They actually read the paper and tried to synthesize, you know, the discipline and statistics perspectives. So yeah, it's a
Yeah.
much more thorough, like I just refereed a stats paper for one of the AppJ journals. It was submitted to letters and, you know, wrote a really lengthy review. It was a very bad paper. The authors revised it, and the editor decided to accept it without further review and to publish it in a special AppJ sup issue on astrostatistics. And when I've only briefly looked at the revised paper, but there's still a lot of wrong stuff in it. But now it's going to be in an AppJ sup that's its special astrostatistics issue. So it gives it this air of authority when it hasn't really been thoroughly refereed. It's just crazy.
Yeah, I'm glad you said it, because I didn't want to say it, but yeah, it seems to me like yeah, there is a disconnect here. Anyway, and then, for example, I'm being a member of the American Statistical Association. I think I don't know, was it a couple of years ago that the new data science in science, there are in a large number of journals, that has the data science word in it. That might be I don't have experience actually with that type, what type of refereeing is done there. But that this seems to be coming up. Certainly, I don't think many of these were there maybe 10 or 15 years ago, or anyway. And then there are I think that then there are other journals, like for example, I had this is born out of personal experience. For whatever it's worth, I had a relatively small paper on some distribution that came up in the process of doing my statistical analysis, and pretty much I didn't know where to publish it, right? That's the kind of, relatively small, for example, and there are many journals, including the broad scope. I don't know what PLOS stands for. Is it public? No, a library of science. I can't. No, I can. Anyway, for example, is it? Tom? Maybe I shouldn't talk about things I'm not. But for me, I remember submitting it to PLOS one. But they wanted like $3,500 for that tiny 4 pages paper. And quite frankly, I got it accepted after 3 weeks, but I said, I can't pay the bill. Okay. And that's, I don't know. Anyways, that was my experience with that journal. But, probably it seemed, no implication that, anyway, that's just personal experience. For example, our proceedings will be published as part of Frontiers in Astronomy and Space Science / Astrophysics, Astrostatistics, which, to my knowledge, by the way, is the only journal that has the word astrostatistics in it. Okay, you can Google, right? And I believe that that's the only one. I was an associate editor for a few years. Now I'm like special editor along with Vinay and others, for this edition. Okay, and then of course, I mean, so many journals are cropping up right now. And again, I did it as a social experiment. I submitted, a short paper to 3 or 4 of these journals, and I got it back with an acceptance within 3 days. Okay, with obviously no peer review, anything. So which kind of begs the question ultimately, what does it mean to publish a paper, right? And that's kind of like what I was thinking this morning when I wrote this done. And anyways, that's really all I had. I wanted to just share those few thoughts here.
I just want to make one comment about this. I mean, Tom, I forgot the name of this journal, that the special issue that we are supposed to edit. Do you remember SD spatial something or the other?
Oh, you mean the image thing?
Yeah.
Oh, hold on a second. This isn't here, huh? I thought I edited.
I don't remember it either. We're about to have our first meeting.
Yeah. So just to, many people here are probably going to be interested in this. It is, here it is, I found it. The special issue of the Statistics and Data Science and Imaging. It's going to be called Astrostatistics for Imaging Data, tentatively. But the imaging, any sort of spatial analysis, I think it's going to be a good thing for, if you want to submit to it. So sorry, because I thought how do you tell people where to submit? I mean, we want to find out in about a week or so, more details.
For this conference?
For people who are here, I think they would be really interested in this.
Post on the slide.
Oh, for your issue, the one. Yeah, I think what I was planning to do is maybe as early as tonight, meaning that once you guys get home, I will remind you, please submit the proceedings, and maybe I will do that alongside with
So
the
before we're
information.
in the proceedings?
No, separate. I was trying to say that maybe in the same email I can remind them.
No, we won't have the submission details for at least another week.
Well, then we can wait a week.
Okay.
Yeah.
All right.
Yeah.
Fair enough. Right.
Maybe that one. Maybe.
I'll just tack on machine learning, science, and technology, which is not on that list, but I published in there before and had a decent time with it. The review process was good.
Anyways, I'm not sure if there is anything else here that we want to.
I'm a fan of archive.
Right. Yeah, for example, right, yeah, I didn't touch it explicitly on. Oh, certainly, I was wondering whether, what's the general, sense whether, when you find a paper that, even if it's not published, it's all good.
I usually, for at least I feel the applicants stuff is when we submit to a journal,
Right.
post on archive the same thing, and then after this, the few edits get published, you'll update the archive with the edited published versions,
Oh, sure, but
just so you don't get scooped. But there's another instance with that, Dr. Eric Burns talked about the line in the spectra.
yes.
The original paper was very confidential, and through the instrument team, we did a very deep, thorough analysis, but we didn't want to take away from their discovery. So our thought was, we'll post on archive and do a I forget what it's called, but something letter in Active, but it's not refereed. It's basically
Well,
so that
Oh, the research.
The research notes and info. Yeah.
Because we didn't want to take away from it, wanted to very much point to this paper found it. We're just confirming it as the instrument team that we agreed with it.
Yeah,
We used archive that way and it worked pretty well.
Yeah, I personally like. I think it's still active. The research notes. There have been a few instances in which I wanted to add a couple of pages that felt like an actual publication because it says AAS, right? But still, it's not really refereed anyways.
Chris Lintott is the main editor for it, and he just posted a
you, yeah.
blog. He just posted a blog on it a few months ago, noting they just had their 2000th publication, and he was strongly encouraging people to keep submitting stuff. The papers there are not refereed, but they are moderated by the AAS editors. And one of the interesting things I actually just posted on a statistics blog about this as a commenter is that he strongly encourages people to publish null results there. And it seems to me it might be the only journal that actually invites null results.
Yeah, and I believe that
Interesting idea.
Chris Lintott, he's also usually the editor of choice for any paper that comes to APJ that has substantial statistics in it. So, anyways,
Actually, the point about archive is a really interesting one right now because I don't know if folks saw it, but CS Archive
Oh, yeah.
has banned non-refereed papers from appearing on archive.
Oh, I didn't know that.
It's no longer a preprint server for CS because they're saying they faced a deluge of AI generated papers and they're trying to cut down. So they require something to be peer reviewed before it hits archive. And I think right now they're soliciting inputs for what to do in other fields. But it's an interesting question because, I mean, how do you reduce AI generated slop while still getting the value from a preprint server to see early results, to get feedback from the community that you can work into improving your research? I don't know.
yeah, because definitely right. What you were saying, Stephen, this is what I've always done as well. Most people just put the preprint, knowing that it would be published, so you don't feel bad about it, right? Pretty much. But and yes, and in fact, Alex, Vinay just told me, was it last night about the computer science, not being so. Yes, this is was completely new to me, and that's probably implicitly how that little bullet ended up there just to bring it up because pros and cons for sure. Yeah.
One thing, there's the open journal policy.
Uh-huh.
It's basically does everything for archive. They don't have any keys as far as I know, but in archive, there is a section for instrumentation and data for Swan.
Uh-huh.
So I think that's one way that is, you know, retrieve by being an archive of this open journal collection.
I didn't know about that. I think I heard about the name Open Journal of Astrophysics, but I didn't realize that he was doing that. Okay.
Yeah, I think it's legitimate because there are some well-known people on there for the board. But I don't know how long, like, this is, we don't have any communication charges with it now, but how long can they take this, how far can they take this? Things to be seen, but it is a good option or something like that. So if something like this, framework. It also gives you, it's different if you put it in your publication, it's just an archive link, but if it says publish in group and then this.
Right, right, right. Um, okay, so I think that Vinay is signaling that he needs to catch his flight, right? And that obviously that seems to be more important than arguing about things. And so this might be a good point to just say once again, thanks absolutely so very much to everybody. Okay, and who knows, maybe see some of you, most of you, all of you in what, not a year or two somewhere, maybe Alabama, maybe somewhere else, and do more statistics. So thank you so much, and yeah.
Thank you, Max.
Absolutely. Thank you. Yeah, this is fun. Yes.
That was fun. Thanks.
Absolutely. So here, I guess
Appreciate the